Okay, we'll come on to just the final few questions of the investigation paper, and you can see the type of shape now has changed. We're moving into a different regular polygon. So we started off with a rectangle, and then they moved it to a square, which if you think about it is a regular quadrilateral, all sides the same, all angles the same. And now we are moving into a regular hexagon. So Lee draws a circle on a piece of paper in the shape of a regular hexagon with side length x. The circle touches all 6 edges of the piece of paper. Right, just from observation, you can see gradually these circles are starting to cover more and more and more of the shape. It may be useful for later. Lee drops grains of rice at random onto the paper. He counts the number of grains of rice inside the circle and finds the relative frequency. Find an estimate for the value of pi when x equals 30 and the relative frequency that the grain of rice is inside the circle is 0.905. So we don't need to go flicking back because it tells us use the formula area of circle over area of paper equals relative frequency. So we know this relative frequency, we've just been given it, which is 0.905. We're probably going to have to work out some areas, which I think the circle will be okay, but the other one will be an issue. So we have been told that x equals 30. So I'm just going to write this down. X equals 30. Then we've got this root 3x over 2. Right, so if we think about root 3x over 2, x is 30. So this radius here, in fact, I might just draw it here so I don't get overrun, but it's root 3 times 30 over 2. So root 3x over 2 when x is 30. I'm just going to write that down. You could just say, well, it's 30 over 2, 15. 15 times root 3 is 15 root 3. If you're not comfortable doing that, then just put it in your calculator. So this is the radius. Right, so area of circle. And remember, what we don't want, because this whole thing is about investigating the value of pi, what we don't want is an area of circle that puts the pi in as a number. We definitely want this to be something pi. So it's r squared times pi equals, or r we just said is 15 root 3 squared times pi. So you could just leave it like that, or we could go to our calculator and we could do 15 root 3 and then square it. Like that, and that comes at 675. So actually the area of the circle is 675 pi. So that's quite a nice number. The area of the hexagon is going to be more complicated. Now, whenever you're trying to find the area of a regular polygon, and you have kind of the radius, so if you've got either it's drawn inside a circle or a circle's drawn inside it, your best bet is to split the thing into triangles. So I'm going to draw a few triangles here. If I kind of do that, so if I go to the corners, say I went down all the way around here like that, and I just keep going, what you'll find is you've split the thing into 6 triangles. For a hexagon, they happen to be equilateral triangles. So that kind of gives you an option of using the half times side times sine of the angle between them. You've got 2 choices. You can either use this perpendicular line, which actually splits this big triangle into 2 half triangles with a base that you can work out and height that you can work out. Or you can, as I've just said, you can use your half times side times sine angle. I'm going to use the right angle approach because I just think it'll probably make more sense to more people. So basically this triangle here, if I just draw this like that, well, it's got this was x all the way across. This perpendicular splits it in half, so this is x over 2, or in our case it's 15. The height, well, we've been told that's root 3x over 2. So in our case, well, x was 30, so 30 over 2 is 15, so it must be 15 root 3. Like that. So just check 30 over 2, 15, 15 root 3. Right, so for the area of paper, well, you've got to work out how many triangles there are. So if you think there would be 6 of these big triangles, so this triangle's half of that is going to be 12 triangles. So it's 12 triangles times, and then just the area of one triangle. Remember, it's half times base times height. But because we've got a 90 degrees here, this can be the base and this can be the height. So a half times base is 15 times height, we said was 15 root 3. And actually, just because this isn't, I don't need to wrestle the algebra so much, I'm just going to put that into our calculator. So I might do a 12 times a half is just 6, and I'll probably put the rest in. So 6 times 15 times 15 times the square root of 3. So that comes out as 2338.26859. So that's the area of paper. So now we need to find an estimate of pi. So remember, our formula is area of circle over area of paper equals relative frequency. So area of circle, we've said, was 675 pi over area of paper, 2338.26859, equals relative frequency. We've been told it's 0.905. So pi must be, or the estimate for pi, sorry, would be, well, it's this 0.905 times this 2338, and so on, I won't write it all in, over 675. So hopefully that will give us something close to 3.14, otherwise something's gone wrong. So 0.905 times 2, try and use all the accuracy of the numbers, so 2338. Actually, I probably should have used the A and S key, but it's a bit late now. Do look for opportunities where you can do that. It saves you doing what I'm doing now. It's 26859. All over 675 should leave us with pi. Okay, well, that's not bad at all, is it? So that is equals, does it ask us for accuracy? So it equals here 3.1350 ... So to 3 significant figures, it actually is 3.14 to 3SF. Very encouraging. Show that for any value of x, the estimate for pi equals k times relative frequency, where k is an exact constant. So the word exact means that it's going to have probably surds in this case. I wouldn't normally say pi's, but the fact that we're calculating a pi, there's unlikely to be a pi in the answer, but things like surds and pi's, and later on you'll have things like e's and stuff like that. To do some algebra, but we have been given a bit more space here. Right, let's find the value of k. So we still know, we know quite a lot from the last question. We actually did quite a lot of the setup work, if you think about it. We've still got to use this formula, area of circle over area of paper equals relative frequency. We know the area of the circle is going to be r squared times pi, and we know that r is root 3x over 2. We also know that to work out the area of the paper, which is hexagonal, we're going to do it using these 12 little rectangles. 12 times a half times base times height. Now the base and the height have changed. X isn't 30 anymore, x is just x. So the base is x over 2 and the height is root 3x over 2. So let's write some expressions down. We'll start with the circle. Area of circle, remember it's r squared times pi, and I do keep checking back, so I really don't want to make a mistake. R is root 3x over 2. So it is root 3x over 2 squared times pi. Well, that is, we can do quite a lot on that. It's root 3 over 2 squared times x squared. Root 3 squared is 3, x squared is x squared, so it's 3x squared on the top, and there's a 2 squared on the bottom, will be a 4, over 4 times pi, like that. That's the area of the circle. Now the hexagon, area of hexagon equals, right, so I'm going to use the formula we used before, which is 12 times a half times base times height. So I'm just going to write in 12 because there's 12 little triangles, the right angled ones, times a half because area of triangle is a half base times height. So now I just need the base and height. Right, so for our little triangles, I've written it here. Remember, the little triangles are these. The base is x over 2 and the height is root 3 x over 2 times x over 2 times root 3x over 2. Okay, so what can we do with that? Well, we could say 12 times a half is 6, then 6 over 2 is 3, so this is kind of 3x times another x, so you end up with 3 root 3x squared over 2 equals, right, so that's not too bad. Right, so now we have area of circle over area of hexagon equals relative frequency. So that means we need something like area of circle over area of hexagon. Area of circle. I'm going to put divided by area of hexagon. So, and see what we can simplify. So it equals 3x squared over 4 pi, I'll keep the pi on top, divided by 3 root 3 x squared over 2. So hopefully you know that to divide by a fraction, you multiply it by the reciprocal of the fraction. So that is 3x squared pi over 4 times, flip this, 2 over 3 root 3 x squared. So now that is area of circle over area of hexagon. Right, so if we're going to solve this for relative frequency, well, let's just see what we can do before. Can we do any cancelling? When you've got something like this, you can cancel any top number with any bottom number. So the 2 and the 4 can become a 1 and a 2 for starters. 3 can cancel with a 3, 1, 1. X squared, 1, 1. The pi stays. So on the top, you've literally just got pi. On the bottom, we have 2 root 3. So now you have, so area, remember, area of circle over area of hexagon. Area of circle divided by area of hexagon equals relative frequency. So area of circle over area of hexagon is pi over 2 root 3. So pi over 2 root 3 equals relative frequency. Okay, so that means pi must equal 2 root 3 times relative frequency. Well, not pi, the estimate of pi equals 2 root 3 times relative frequency. So k must be 2 root 3. Right, so for the final part, Lee draws a circle on a piece of paper in the shape of a regular polygon with end sides. So just remember what I said about investigations. They start with something really basic. We started with this circle. Remember the circle in a rectangle, really crude. And then they make it a little bit more sophisticated. We had the circle, can't find it actually, but, oh sorry, there it is. We then had the circle inside a square. So we're making the thing a little bit more, it's a regular quadrilateral. Then we said, what about a regular polygon with more sides? So the same method, but we're getting more and more sides. Now what you'll find is, with regular polygons, the more sides you get, they get closer and closer to being circles. So the question we're being asked, or what he does, the circle touches all end edges on the piece of paper. It's the same as before. He drops grains of rice at random onto a piece of paper. He counts the number of grains of the rice inside the circle and finds the relative frequency. Estimate for pi is k times relative frequency, as it always was. So explain why the constant k gives an approximation for pi as the value of n increases. So remember what I was saying, what's happening with these shapes? As we're getting more and more sides, these are getting closer to being circles, and the circle is nearly sort of filling the whole shape. So if you're dropping these grains of rice, they're nearly all going to land in the circle. And imagine if this had, say, 12 sides, if it had 15 sides, if it had 100 sides, it's almost going to look identical. You're going to have hardly any bits that aren't circle, that the circle doesn't cover. So the polygon is becoming the circle gradually. It's getting closer and closer and closer to the circle. And the more sides you have, the closer it will be to a circle. So remember, area of circle over area of polygon, we're saying that equals relative frequency. Well, that's our best approximation. So theoretical probability that the rice will land in the circle equals relative frequency, as in the probability experimental that it actually did. So our area of circle, remember, is r squared times pi over area of polygon equals relative frequency. So if we wanted to find our approximation for pi, remember pi, the estimate for pi is relative frequency over r squared. In fact, is area of polygon times relative frequency over r squared, right? That's our estimate for pi. Now, what you will find is, as we have more and more sides, what will happen? The relative frequency, as I said, they will nearly all land in here. So the relative frequency, as in the experimental probability that a grain of rice actually landed in a circle, will get closer and closer to 1. So as n gets larger, this will approach us. So I'll write it really mathematically, but you could get away with just writing somewhere. So as n gets larger, I won't write the full limits and the infinity and stuff. As n gets larger, relative frequency goes towards 1. Relative frequency will get closer to 1 because most of these things will land in the circle. Closer to 1. And also, the area of polygon gets really close to area of circle. So that means, if you think about it, if we're saying this thing here is getting close to pi r squared, we can sort of call that pi r squared. The relative frequency is getting close to 1. You end up with pi, the estimate for pi, is pi r squared times 1 over r squared. If we cancel off the r squared, you can see why suddenly this is getting really, really closer to pi as n gets bigger and bigger and bigger. So I hope that makes sense. The last question's always really tough, but hopefully you're all right with the rest of the walkthrough. You're never going to get an easy last question, but you will hopefully be able to pick up a lot of marks on the way.